Hi. In this video, I'd like to show you how we can make sense of motion in our world using forces. When the idea of force vectors is applied to objects in our world, objects behave in predictable ways. So a tug of war match is really six forces battling against each other. Riding a skateboard is really a matter of your gravity and normal force and also friction and any applied forces. A cat on the sidewalk is going to have forces like gravity and normal. Typically, objects have multiple forces acting on them simultaneously. The effect of an individual force is often reduced or canceled by the effect of another force acting simultaneously. This is an important idea in physics. When you have multiple forces acting, one of the forces might be reduced by another force going against it. In the case of the tug of war, you might end up having all six forces balancing out completely, and you have no movement whatsoever. Or maybe one of the forces edges out the other five, and it starts to accelerate. So, the idea behind all of this is something called the net force. And I wrote this big because I wanted to emphasize just how important this idea is in physics. The reason why it's important is the overall effect of all the individual forces acting on an object depends solely, only on the net force, or the vector sum of the forces. In other words, the net force is the amount of force that's left over after all the individual forces have been added up together and canceled out appropriately. So let's look at this example of a jar. And this jar on the left side of this table, there's three different examples where the jar is being pushed with two forces individually, two different forces. On the first one, we have a force of 10 newtons and a force of 5 newtons, both acting to the right. The net force, the leftover force, if you add up these two together, since they're both going in the same direction, the net force is 15 newtons to the right. However, if the forces are acting against each other, the 10 Newton force is a little bit reduced by the 5 Newton force. The effects are not quite as much as they could be, so the overall net force here is 5 newtons to the right. It's what's left over. And then finally, if we have two forces that are equal and opposite of each other, they end up reducing each other completely and canceling out their effects altogether. So the forces are still there, but their effect has been canceled by the other force. And so the net force would be 0 newtons. The reason why these net forces matter so much is each time the jar accelerates as if the net force is the only force acting on it. So we can analyze the motion of an object solely based on the net force. If we can figure out what all the different forces are individually and find out the overall leftover force, that will tell us exactly how the object will behave. It's always based on the net force. So one of the ways that helps us keep things organized when we're dealing with lots and lots of forces and different directions and all that is something called a free body diagram. We often use arrows to represent both the size and the direction of a force. And so when we have multiple forces acting on an object, we're going to have multiple arrows. This car is traveling to the right, and there's an applied force from the engine pushing it forward. There's also some air resistance against the car's motion. The car also has a weight from gravity, but the road also supports the car, so there's a normal force acting on it. So there's four forces shown here. In the scope of our class, we're just going to stick to four forces acting on an object, and we're going to keep it pretty simple. Of course, there are more complex ways of working this out, but we're going to keep it as simple as necessary for the scope of our class. To make situations more clear, instead of using a car, we often just represent the object as a dot or a box. And this helps us to kind of visually see the force vectors more clearly. This is what we call a free body diagram. So we take the picture of the real world scenario and we reduce it down to a box or sometimes a dot right here. And then we draw force vectors away from this box. force vectors are always drawn from the object and extending outwards away from the object in the direction of the force. So this helps us to see, okay, overall, it looks like the gravity and the normal are equal and opposite, and so they would reduce each other to zero. And it looks like we have a little bit more applied force than air resistance, and so the net force is going to be in the rightward direction. All right, let's look at a couple of examples with numbers. So I've got two free body diagrams here. Let's look at the left one first. So this object is falling, and I know that because we have gravity pulling it down and there's air resistance acting against its motion. It's falling down, so the air resistance is pushing up. And I have numbers here to represent how much force is acting. We have 75 newtons of weight, 25 newtons of air resistance. The net force here is 50 newtons with the downward direction. You have to indicate the direction here because force is a vector, and I forgot to write my vector symbol there to show that we include the direction. So you can write 50 newtons down, or you can write negative 50 newtons, and we understand negative to mean down in this case. Over here we have a free body diagram with 4 forces acting on it. We have friction, 5 newtons to the left, normal and gravity are both 10 newtons, and then the applied force is 20 newtons to the right, similar to the car that we just saw. So in this case, the gravity and the normal are perfectly balanced. So we say the vertical forces are balanced here. They're not going to play into the net force because they perfectly balance each other out. So all we have to concern ourselves with is the friction and the applied force. So 5 newtons to the left, 20 newtons to the right. Overall, that's a net force of 15 newtons to the right. So for the scope of our class, we're only going to be dealing with force vectors where you have one of the sides, vertical or horizontal, just balancing out completely, and left over we just have either a horizontal force or a vertical force. So we're not going to have we're not going to have net force in 2 different directions. It's always going to be along one of our directions. So that's all I've got for you in this video. Remember, happiness is not having what you want, it's wanting what you have.